All right, so we're going to continue with question number 26. A red and white striped t-shirt is viewed in red light. What color would it appear to be? Okay, so what you want to remember is that when it comes to pigments, the color of the clothes or the shirt, it will absorb all other colors except its color. So for example, if you shine blue light on a blue shirt, then it will reflect that blue light. But if you shine red light on that same blue shirt, it will absorb the red light. And of course, if no light is reflected, then you will see nothing. You would see the absence of color, which is black. Okay, so let's look at each one of these. So if the shirt is a red and white striped shirt, okay, that means we have strips of red, okay, and all the other parts of the shirt are white, and these portions are red, okay, and it's being viewed in red light. So the light being shown on it is red, okay. So the parts of the shirt that are white are going to reflect that red light, okay, because what is true for black, when you see black, you're having all the colors absorbed, but when you see white, all of the colors are reflected, okay. So white reflects all colors, black means all the colors were absorbed, so white reflects all, black means all the colors were absorbed, and any color will reflect itself only. Okay, so red reflects red, green reflects green, so on and so forth. Okay, so the white parts are going to reflect the red light back, so it's going to look red. And the red parts will reflect its color as well, so it will look red. Okay, so both parts of the shirt, the white parts and the red parts, will look red. So the shirt will look completely red, solid red. Next question. A student uses a converging lens to project an image of a distant object onto a screen. Which of the following image properties describe the image observed by the student? Okay, so let's remember a converging lens. Converging, that's our convex lens. Convex, X marks the spot. So this is the one where all of our light rays are refracted and they meet at a point like so. Okay, we already have a clue here as to one of the properties of this image. Okay, we know that it can be produced on a screen, and that only happens for real images. Okay, so we can go ahead and eliminate one of these options. Okay, because we know that the image produced by this lens is going to be a real one. Virtual images are produced by the other type of lens, the concave lens. So that's your clue. Now the next thing you need to know is it diminished or magnified, and is it upright or inverted? Okay, so another thing, real images are always inverted, so you can eliminate one more option. Okay, and finally, if you don't remember this from doing an experiment, you might just want to jot this down and memorize this, because this is the case that you're typically going to be asked about on this paper. Okay, for a distant object, it's going to be real, it's going to be inverted, and it's going to be diminished. Okay, diminished meaning smaller than the object, inverted meaning upside down. All right, so we have a light ray incident upon a plane mirror. Remember, plane mirrors, those are flat, like the ones you use in the bathroom or in your room every day. And we have an angle of incidence of 30 degrees. What will be the angle of reflection? Okay. All right, so we have question number 28 says the diagram shows a light ray incident upon a plane mirror at 30 degrees to the mirror. Now, you want to put a little caution mark here, This is a common mistake that students make. Remember that the angle of incidence is measured between the incident ray and the normal. Always, the normal has to be one of those lines that make up the angle. And the angle of reflection is going to be on the other side. It's going to be the angle that's made from the reflected ray. So this will be our reflected ray and our normal. So what's this angle? Okay. Well, if you remember what you know about right angles or angles at a point, depending on what you're given, you know that anytime you have two lines that are perpendicular, they make a right angle, and a right angle is equal to 90 degrees. Okay. So what I'm saying is that this entire angle here is 90 degrees. And if you know a part of it, you know that this part is 30, then we can just do a simple operation, just do some subtraction, and we'll be able to figure out what this angle is, our angle of incidence. That's the one we want. So we say 90 minus 30 degrees, and that's going to give us 60 degrees. So our angle of incidence is 60 degrees. But we're asked, what will be our angle of reflection? We have to know one more thing. We have to know the law of reflection, which tells us that the angle of incidence is equal to the angle of reflection. Okay, so here there are a couple parts to this question. Number one, we have to recognize that this angle was not the angle of incidence. That's just the angle between the mirror and the ray. We needed to remember that the angle of incidence is measured between the normal and the ray. Similarly, the angle of reflection is measured between the normal and that reflected ray. We also needed to remember that the mirror and the normal make a 90-degree angle. So if we know the angle between the incident ray and the mirror, we need to subtract that from 90 degrees in order to find the angle of incidence. If the 30 degrees was over here, we would do the same thing, because this is also 30 degrees. Because if you remember, angles at a point or on a straight line all add up to 180. Okay, so you can figure that out as well. Okay, so our answer here is going to be C, 60 degrees. All right, number 29. Which of the following instruments uses optical fibers? Okay, so at first glance, you may not know this, but we can do a little process of elimination. Okay, so what's an anemometer? Did you say an instrument that measures wind speed? If you did, you are correct. Not to be confused with a barometer that measures the amount of atmospheric pressure or air pressure. Okay. And what about this one? Got to use a little bit of our context clues. Seismograph. Well, that sounds like seismic. And I remember that that was related to longitudinal waves. That has to do with earthquakes. Okay? So seismic waves are what are produced when we have earthquakes. They're a type of longitudinal wave. So a seismograph is an instrument used to measure earthquake waves. So we've done our process of elimination. It's not A, it's not D, it's not B, it's C. Okay, it's endoscope. You might want to jot that one down in case you haven't heard of that before. So an endoscope is an instrument that is used in medicine, okay, and it uses optical fibers to get special pictures of tissues and other structures inside the body. Okay, and last one for this video. We have a light ray entering a 45, 90, 45 prism along a normal line shown. So this is a right-angled triangular prism. Okay, so this is a special case. This is kind of where reflection meets refraction. We got to know a little bit about both in order to understand why what happens actually happens. So we have an incident ray, okay? And it goes in, this red line is our normal. Okay, and that blue arrow represents our incident ray. Notice that our ray lies exactly on the normal. We have a special term for this. We call this normal incidence. The ray is moving from air to glass, and so we would expect it to bend, right? We would expect to get refraction because we're having a change in medium. But when the angle of incidence, okay, is equal to 90 degrees, in other words, it lies on the normal, then we have no deviation, no refraction. It just goes straight in, okay? So you might be thinking, if the incident ray passed from the air to the glass, then it's just going to keep going. It's going to come out again, right? So you might be thinking that your next ray, your reflected or your refracted ray, would look something like that, or like that. It goes out. Okay? Well, no, that's not what happens. And the reason that doesn't happen is because every medium has a specific angle, and if the angle of incidence is greater than that, then the ray is not going to be able to escape or be refracted and pass into the next medium. It's going to be turned around and it's going to be actually reflected right back into the same medium. So if we look at the angle of incidence, let's call this wave that's now in our glass prism. This is our new angle of incidence right here between the green and our red normal. I'm going to color it in pink. Okay, that's our angle of incidence, making an angle with the normal, the red normal there. That angle is 45 degrees. But in order for us to get refraction in glass, the angle has to be less than 42 degrees. Okay? Other way around. The angle has to be less than 42 degrees. This is what's called the critical angle for glass. Okay? Other materials will have a different value for this critical angle. But anytime that you have an incident ray coming in at an angle greater than that critical angle, whether it's 1 degree greater or 10 degrees greater, what's going to happen is we're going to get an effect called total internal reflection. Okay? And even though we use the word reflection, what's actually happening is it's being bent so far that it's being bent in the opposite direction. So we're going to have our refracted ray coming out like that. Okay? And so that's where it would emerge from. It will do a complete 90-degree turn. Okay? And you can do a little bit of geometry to prove that this is 45 degrees. Okay? But if you know this shape, okay, if you have two 45-degree angles here and all triangles add up to 180, then this must be your right angle triangle. That's the only way, that must be a right angle. That's the only way that you can get that triangle right there. Okay, that triangle. And there's your 90 degrees. And so this angle here is 45, just like the shape of the bigger prism. So our answer is that this light ray is going to emerge from face ST. Okay, because it have done a complete 90-degree turn. All right, that's it for this video. Continued in the next one.